Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Ladies and gentlemen, my name is Dr. Hina Siddiqui. I welcome you all alongside Ms. Fazima at this webinar. I request all the participants to kindly mute their mics so that we can hear our speaker loudly and clearly. Ladies and gentlemen, at Comstech, we are conducting many capacity building work initiatives and activities. One of its kind is the webinar series in which we are right now. Many eminent speakers and champions of their field have spoke at this forum. Today, we have yet another eminent speaker and very prominent scientist with us, Professor Dr. Farid Aburaghe Mohammad Haris. And it's my pleasure to introduce Professor Farid to you all. Professor Haris is currently Najran University, Saudi Arabia, and professor from the Advanced Material Department, Central Metallurgical R&D Institute, Cairo, Egypt. He got his PhD in physical chemistry from Kyoto University, Japan in 2003. Professor Haris was a JSPS fellow at Kyoto University during 2003. He is visiting scholar to Department of Material Sciences and Engineering, University of Delaware 2011 and University of Florida, USA 2009. He was awarded Encouragement State Prize in Advanced Technology Science 2009 and Environmental Science Award 2012 and the award of Professor Sama Al-Kholi in Environmental Science 2016 from Academy of Scientific Research and Technology, Egypt. He has also received first award of Federation of Arab Scientific Research Council for outstanding scientific research in nanotechnology 2014 and publication award from Misr Al Khair Foundation Egypt 2010 and 12. He is masters in electrochemistry, physical chemistry, material chemistry and nanotechnology. Professor Haris has authored around 230 papers, 110 peer-reviewed in academic articles, 77 abstract and proceedings in international conference and 50 national conferences, 3 book chapters and 1 US patent with an H index of 34. He has total citation 2,707 according to Scoopers. With this, I welcome Professor Farid for his talk. Over to you, sir.
Thank you, Dr. Siddiqui, for introduction. And first of all, I would like to thank very much the organizer of the event. And actually, it is my pleasure and my honor to be participated in Comstech event as a speaker today. Today, my talk titled Nanomaterials for Sensor and Photochemical Applications. First of all, let me just a brief introduction about Najran University and the Najran City. Najran City locates at the south part of Saudi Arabia, and Najran University was established in 2007 in a temporary place, and we just moved to our new campus in 2014. The campus is the largest campus in Saudi Arabia, and it locates in the eastern part of Najran City. The campus contains about 15 colleges for male and 10 colleges for female, with a total number of students around 45,000 students. At the beginning of the establishment of Najran University, the management structure of the university established also a Nano-Research Center in 2009. And the Najran University supports the Nano Center with fund allocation for infrastructure and instrumentation, including a laboratory for clean room technology. Also for human resources, the higher experienced scientists, both in Saudi scientists as well as non-Saudi scientists, in addition to professional, technical, and administrative staff. The research area of our center, Promising Center for Sensor and Electronic Device, include the sensors, environmental remediation, and the electronic devices, with some sub-activity and task as shown in front of you. Our Nano-Research Center is actually well equipped with advanced research and instrumentation, including SEM and TM, XRD, UV vis, IR, Raman, and electrochemical station, solar simulator, and so on. Also, we have a very fascinating instrumentation in our clean room laboratory, including the sputtering systems, thermal evaporation, PE, CVD, and ICB etcher, and wafer tracking and mask aligner. This is actually used for microfabrication and device fabrication in our clean room technology. In our center, we have a very strong national collaboration with the Saudi University. On the top, King Saudi University and King Abdulaziz University, King Khalid University, and the CACST, King Abdulaziz City for Science and Technology, came to the top priority of our national partners. In addition, we have a very nice and good international collaboration with several universities, with South Korea and the Indian University, Chinese University, USA University, Greek, UK, Portugal, and some Egyptian institutions, in addition to some Jordan university. Now, let me just introduce my topic today. I will give some brief introduction about the sensor and the photochemical application of nanomaterials. And the major part of my talk will focus on the application of nanomaterials in sensor technology. And the second small part of my talk will just concern with the photochemical applications of nanomaterials, focusing on photocatalysis. And then my talk will end with some concluding remark and future prospects. First, our motivation in sensor. Nanomaterials actually, have some unusual physicochemical properties compared to bulky materials. So we try our best to understand the role of nanomaterials and nanotechnology in developing new sensing elements with an ultimate objective to improve the sensing performance. Also, as the majority of the center members are material scientists, the background is chemistry and physics, and sometimes chemical engineer. We are also targeting to investigate on material structure, understanding the operational mechanism, material characterization, and modification, with ultimate objective to make a real progress in sensor technology in terms of sensitivity, specificity, and stability. Now, let me just brief introduce the underlying principle of sensor in general. This is just a schematic diagram of the electrochemical sensor. This includes the body of transducer. This kind of transducers might be an electrode or thermistor. This transducer is modified, chemically modified with some receptor. This receptor is nanomaterials. It might be some enzyme, carbon nanotube, graphene, semiconductor metal oxide, metallic nanoparticles, and so on. And the other part is our targeting analyte, including biomolecules, inorganic molecules, including hydrogen peroxide, glucose, urea, alcohols, and so on. under the exposure of our analyte to the modified transducer with the receptor, some signal appear, we make amplification, and we can detect this signal using some electrochemical workstation. Okay, this is very important requirement to obtain a high quality sensor. First of all, the sensor should be sensitive. Sensitive means we have to receive some high signal to noise ratio. Also, the signal should be changes greatly with the analyte under investigation, and also stable sensor material over time or storage. This is the sensor stability, operational stability, or long-term stability. And also the stability of material itself. The material itself should not leach upon exposure to the analyte, and the material itself during the modification of the working electrode should adequately adhere to the support, and also the process should be cost effective, and the sensor material should be non-toxic, in a way that all of these factors will lead to achieve good selectivity of the sensor or specificity and wide detection range, together with very low of detection limit of our sensor. Now we are material scientists, and we are interested to fabricate and synthesize some nanomaterials. And as I just mentioned a couple of minutes ago, the nanomaterial is lead to some very interesting properties, including physical and chemical optical properties. I just give a nice example here. This is a covered slide. Why nano? Because nano produce very extremely huge surface area of the final nanoscale material. For example, if we have a gold cube with a side length of 1 meter, the total surface area of this cube will equal to 6 square meters. If you divide this side to 1/4 meter, the mass is still the same without any change, but the surface area will increase. If this cube, the side equal 1 nanometer, a huge surface area can be obtained like 6,000 square kilometers. Actually, this total surface area is more than 300 times the area of our new campus of Najran University. Also, there is some hidden parameter for nano material that is called surface energy. This figure shows that the surface energy is increased as the particle diameter decreasing. So when you fabricate nanomaterial, the atoms, the active atoms, tend to be available on the surface. This will reflect a very reactive surface for nanomaterial. Okay, let us now go to the first part of my talk about the sensing application using porous silicon. Porous silicon actually is a promising sensing material, and like alumina and titania, porous silicon can be fabricated via self-organizing using the electrochemistry, by the electrochemical anodization of silicon wafer in some hydrofluoric acid containing some surfactant. Porous silicon actually was first discovered in 1956 by accident at Bell Laboratory by Arthur Orer and his wife. At the time, Arthur did not recognize that the film produced on silicon wafer during the electropolishing is porous silicon in nature. However, the porous nature was first reported by Professor Watanabe in 1971, and in 1990, the most prominent phenomena of porous silicon, that is the photoluminescence, was observed by Professor Canham, And actually, this phenomena of the ability of porous silicon to emit strong visible light at room temperature, this phenomena was never observed in bulk silicon. This is just to show you how to form the porous silicon starting from silicon wafer by the electrochemical anodization in hydrofluoric acid containing some alcohol or surfactant. Optimizing the electrochemical etching and anodization, we can obtain smooth and straight pore walls together with extremely large internal surface area. And if you, with just simple playing with the conditions of the electrochemical etching, controllable pore sizes ranging from nanometer up to a few micrometer can be attained. For people who are interested in porous silicon technology, you have to conduct what is called current potential curve before performing fabrication of anodization. The reason is that just to determine the critical current, beyond it, the electropolishing started to take place on silicon. So you have to determine this kind of critical current to avoid working after the critical current and not to enter electropolishing regime. This is a kind of some nice pictures of porous silicon with various pore sizes and structure, order pores, random macro pores, medium-sized pores, and mesopores. Now, what is the underlying principle of using this kind of silicon pores in sensing? First of all, porous silicon, when it comes to contact with some target analyte, some infiltration of this target analyte can infiltrate into the pores. Now you have two ways. The reflective index of the porous silicon will change. That means the optical properties of the porous silicon will change. Just to follow up this change in optical properties via measuring the reflectivity, and you will get some red shift or blue shift depending on the physicochemical properties of the targeting analyte. In other way, upon infiltration of the target analyte into the nanopores, some change in surface charge will occur. This will change the electrical properties of the porous silicon. You can follow and measure this electrical property change via measuring the capacitance, conductance, resistance, or IE curve. Now, let me give you some example of utilization of porous silicon-based electrical sensor. This is our porous layer. The thickness is around 7 micrometer, and the pore size is around 30 nanometer. It liquids in the mesoporosity regime. Upon infiltration of this porous structure with some target analyte, here, the electrical properties will change. Here, this is we make some thermal oxidation of porous silicon just to make stabilization of the device by thermal oxidation. Upon infiltration of some polar solvent into the nanoporous structure, using, for example, ethanol, methanol, acetone, acetonitrile, or chloroform, you can see that there is a rapid change, rapid increment of conductance as well as capacitance. You can measure this change upon infiltration. And once the porous layer is completely filled and wetted with the organic solvent, it reaches to the maximum level, okay? Then leave the device at room temperature, then the organic solvent starts to evaporate, and the capacitance or conductance will return to its baseline again after the device is completely dried. When we examine the response towards some non-polar solvent, the behavior, the response of the device is completely opposite to the polar one. Actually, this is actually depend on the physicochemical properties and different physicochemical properties between polar solvent and non-polar solvent. Our device is also responsible for water, and this is very interesting because our device can be utilized to detect some aqueous analyte. Here, this table shows some different sensor response with some polar and non-polar solvent, and it is discussed due to the different dielectric constant, dipole moment, and the polarizability of the polar or non-polar solvent. Our device is stable, and we have been able to repeat the use of the sensor for several cycles, and the capacitance response retains around 92% from its initial value. And also we observed minimal aging effect, storage effect for our device. Now, we recently tried to make another progress on terms of sensitivity and response time via modification of the interface. Our strategy here is to make some conducting polymer infiltration inside the nanopores. We can obtain some nano hybrid with conducting polymer with the porous silicon via spin coating and or electropolymerization. And this structure of porous silicon filled with conducting polymer is very interesting. And recently we got some interesting result during the methanol sensing via capacitance change. The most interesting sensing observation using this porous silicon infiltrated with conducting polymer is that the capacitance change was found to be 10 times the previous one without conducting polymer infiltration. And also we make some very nice metallic contact, front metallic contact to our nano hybrid porous silicon based device. And this is running research. Second example concerning to the utilization of porous silicon as active surface enhanced Raman scattering active substrate. This technique actually substrate is very interesting technique and fascinating to just sense various target analyte with very low concentration level. We just make a modification of porous silicon with silver nanoparticles with a very simple chemical process, and we got some active substrate during our sensing and detection of crystal violet dye. A detectable concentration down to 0.1 nanomolar is obtained with some enhancement factor with 1,000,000 times. This work has been published in Applied Surface Science. And recently we submitted some interesting result to scientific report. It is under review, and it is utilization of porous silicon decorated with palladium nanoparticles and use the structure to detect some pesticide, imidacloprid pesticide, with some detectable concentration with 1 nanomolar and the enhancement factor with the range of 10 to 5 times. And the last example of SERS active substrate is the fabrication of gold nanoparticles, modified mesoporous silicon substrate, and we have successfully used this substrate for the sensitive detection of horseradish peroxidase enzyme, and this work has been submitted under review in Chemosensor. Now, another example to the porous silicon nanopowder based electrochemical sensor. We have also make a modification of porous silicon nanopowder. This is actually different from the previous porous silicon. The previous porous silicon was porous silicon film or layer fabricated on the silicon wafer. But here, the strategy or the sensing strategy is a little bit different. We start our fabrication using some silicon micro particles, powder, make a stain etching process, fabricate or obtain porous silicon nanopowder, then make some kind of immersion plating to deposit silver nanoparticles into the porous silicon nanopowder, and finally we obtain silver nanoparticles decorated porous silicon nanopowder. We use this powder, and using some binder, we can fabricate some base and make a casting into glass carbon electrode, and we use this interesting structure and modified working electrode to make a sensing for ascorbic acid sensor using electrochemistry, especially amperometric technique. This is the electrochemical performance of our sensing material modified electrode. It's, there is great enhancement in the in the electrochemical activity of our modified electrode. And this is the amperometric detection of ascorbic acid. This is a very interesting result we have obtained. The sensitivity of this sensor is very good, with a response time less than 5 seconds and a wide linear range from 20 micrometer up to 600 micrometer. And the limit of detection of our sensor device is very low, with excellent selectivity. In addition to that, we have validated the performance of our sensor device using some vitamin C tablets. This work, actually, we filed a US patent, and it is recently officially issued in October 2020. Another example of just modification of mesoporous silicon using some carbon nanotube, single wall carbon nanotube, and use this active material as efficient non-enzymatic glucose biosensor in determination of glucose in human blood serum. This is just the material characterization of our hybrid nanomaterials. And this is also the material characterization using XPS. And this is morphological study and elemental study to confirm the coupling between carbon nanotube and porous silicon nanopowder. Then we examined this nano composite of porous silicon with single wall carbon nanotube as a glucose biosensor via 2 different techniques: amperometric sensing and voltammetric sensing. And we got a very interesting result in terms of sensitivity. Sensitivity here is not very high, it's acceptable, it's not competitive to the published data, but the interesting is the response time of our sensor is very fast. It's within 3 seconds. And also we got some good wide linear range of operation with very low limit of detection, and the selectivity of our glucose biosensor is actually unique. And this is just to show that, to make sure that our glucose biosensor is stable. Stable means operational stability and storage and long-term stability, and the data is reproducible, and repeatability of the sensor performance is good. And this is the sensor validation, in human blood serum. As you can see, the green column, compare please the green column to the red one. The measured glucose present in human blood serum and measured by our proposed biosensor is very close and in a good agreement with the glucose level measured at the hospital by pathology glucometer. Another example is novel fabrication of just porous silicon mixed or coupled with some mesoporous carbon material, and use this kind of mixed structure as a sensor, electrochemical sensor of ascorbic acid. This is, as usual, the morphological study and the elemental analysis. And this is the electrochemical performance and the catalytic activity of our electrode. And this is the amperometric sensing of ascorbic acid. We got, alhamdulillah, some interesting sensing parameters, including the sensitivity, response time is less than 5 seconds, wide linear range of operation, limit of detection is good, and the selectivity is very acceptable. And we also was able to detect the ascorbic acid from real sample, both in vitamin C tablet as well as in human blood serum. The last example of sensor part is fabrication of mesoporous silicon nanoparticles, modified glass carbon electrode, and its utilization as non-enzymatic detection of dopamine. We detect this dopamine in dopamine hydrochloride injection as well as human blood serum. This is just mesoporous silicon nanoparticles, nothing else. And we chemically modify the glass carbon electrode, and this is our sensor device for dopamine. We got also interesting result during the amperometric dopamine sensor. And this is the detection of dopamine from real sample, acceptable analytical result. And still very fast, example of gold nanoparticles, belated porous silicon nanopowder for detection of hydrogen peroxide. And this work is recently published in Analytical Biochemistry. And this is just to confirm the morphology of our hybrid structure of gold nanoparticles coated porous silicon nanopowder. And this is the voltammetric detection of hydrogen peroxide with a very nice sensitivity, linear range, limit of detection, and the excellent selectivity. We also validated our sensor performance during the determination of hydrogen peroxide in tap water with promising and acceptable analytical result. This is the first part concerning of sensor technology and the application of nanomaterials in sensor technology. The second part of my talk today is photochemical application of nanomaterials, and I will briefly focus on photocatalysis. Let us say the first, the underlying principle of photocatalysis. This diagram shows the titania nanoparticles upon excitation of UV radiation. Here, upon excitation, electron hole pair formation is initially initiated by the band gap excitation of the semiconductor. The holes stay as the valence band of titania semiconductor, whereas the electrons are excited to the conduction band. The electron band can be participated in the reduction process to just make reduction of dissolved oxygen to produce very active species of oxygen radical. And whereas the holes are considered as very active oxidant, can be used to make oxidation for water to produce hydroxyl radical. Both these active radicals can be participated for photodegradation of the target analyte or organic pollutant. This is just pictures copied using the photocatalysis in wastewater treatment. This is the titania photocatalyst as a thin film. And this is a very nice example for solar-based photocatalysis under UV radiation. The point is that titania is the most widely semiconductor used as a photocatalyst. However, due to its wide band gap energy, around 3.2 electron volt, it absorbs only, very small portion of the solar light, around 5% of the solar light, and it is operated in UV regime. So let me show some applications of photocatalysis processes. In addition to the wastewater treatment, the photocatalysis can be used as visible light-driven hydrogen production, especially using dye-synthesized titanium nanomaterials, and also they used to make splitting for water splitting using a new photocatalyst. And the application of visible light photocatalyst also include self-cleaning, air purification, water purification, and antibacterial in wall, floor, or indoor, in addition to the photoorganic synthesis. Now, the question arises, what is the advantage of photocatalysis over other alternative competing processes? Photocatalysis actually lead to complete mineralization of organic pollutant. No waste disposal problem, and no expensive oxidant is needed because the air itself is used as oxidant. The process is cost effective, and the process is operating under mild temperature and pressure. However, the drawback of photocatalysis is the recombination rate of charge carriers is high. And this is actually reduce the photonic efficiency and the photocatalytic performance of the process. A strategy to solve these drawbacks is to find suitable nanomaterials, that is to increase the absorption affinity of the catalyst and to enhance and for better utilization of light, and to make an effective separation of the photo-generated carriers to decrease the recombination rate, and also to enhance the surface catalytic response. For these strategies, there is two main routes to go through them. First route is just to make coupling of two different semiconductor particles in a way that help you to control the band structure. This is a picture show coupling between two semiconductor particles. In this way, charge carrier separation is enhanced. The second strategy is that to just make dopant of semiconductor with some metallic nanoparticles, especially noble nanomaterials. Here, this is an example of the doping of titanium semiconductor with silver nanoparticles. Under this situation, the silver nanoparticles will act as an electron accumulation. Silver here acting as electron sink, electron accumulation, so that reduce the recombination rate between electron and holes, and which in turn will enhance the photocatalytic activity of the hybrid structure and consequently increase the photonic efficiency. I will give you just a very brief two examples of our running work or published work in this area of photocatalysis. The first example, this is example of metal semiconductor composite. We have make a modification of mesoporous silicon with silver nanoparticles and use this hybrid structure for the photocatalytic reduction of chromium-6 as a toxic to less toxic or save moiety of chromium-3 under visible light illumination. This is just the scanning electron micrograph of porous silicon alone and the porous silicon after deposition of silver nanoparticles. This is a TEM micrograph of our silver nanoparticle porous silicon photocatalyst here with some EDX analysis. And this is some interesting result of photo reduction of chromium-6 to chromium-3. And here, under illumination, there is some electron are excited and move to the conduction band. And the silver capture those electron as electron sink and use it during the photo reduction of chromium-6 to chromium-3. The holes remain at the valence band of the porous silicon and can contribute efficiently as oxidant here. In this work, we got photocatalytic reduction efficiency of chromium-6 to chromium-3 above 97% after 3 hours. The second example and the last example of this talk is coupling, fabrication or coupling of two different semiconductor, and using the hydrothermal technique. We fabricated here heterostructure between iron oxide, hematite, and the bismuth sulfide nanorod, and use this hybrid nanomaterials as visible light photocatalyst. This is the characterization, morphological investigation of our hybrid structure. And the interesting here that there is a very nice band alignment between hematite and the bismuth sulfide in a way that enhances the separation of a charge carrier. And upon utilization of this heterostructure of iron oxide doped with bismuth sulfide photocatalyst, we have the ability to make a photodegradation of phenol and the methylene blue without stunting photocatalytic performance. Now I just ask a question and I answer this question. How do I become a nano engineer? In my opinion, you need to have some basic science in nanotechnology. Then you have to get some good skills in chemistry and some good background in physics with some simulation. Then we will be a good nano engineer. To conclude my talk, first part, porous silicon actually is very attractive and interesting sensor in sensor application because the pore size can be tuned. Also, the porosity, morphology, and the thickness can be organized with very large internal surface area. The surface reactivity and functionalization of porous silicon can be attained. And the interesting of porous silicon is it is compatible with the existing silicon microtechnology. However, some challenge in utilization of porous silicon in sensor application is still there, including some creation of good and efficient omo contact, and how to make a surface stabilization of the device, and how to get some ordered pore array and device engineer. If we develop some surface chemistry and fabricate some hybrid structure, we might be able to get excellent sensing performance with long-term stability, which will turn help for possible commercial use. The second part of photocatalysis I can conclude in one point is that the coupling of nanostructure semiconductor with metallic nanoparticles or nanocarbon or conducting polymer could provide an opportunity to develop visible light driven photocatalyst nanocomposite with previously unavailable properties. However, still there is some arising challenge, including how to control the band structure, how to make a good separation, and how to enhance the photonic efficiency and the photocatalyst recyclability. This is a picture of our members in 2015, including some ex-member as well as some current member. And at the end, I have to acknowledge the managing team of our Nano Center of Najran University, including the board of director, the director and the vice director, and our colleagues of researcher and the founder of this Nano Center of Najran University, as well as the technical and administrative staff. And finally, I have to also acknowledge the financial support from the Deputyship for Research and Innovation, Ministry of Education in Saudi Arabia, and also the financial support of Promising Center for Sensor and Electronic Device of Najran University. And at the end, I thank you very much for your attention and the time.
Thank you so much, Professor Farid, for such an excellent talk. And now the floor is open for the questions.
Ma'am, I have a question related to how nanoporous silicone material is giving the signal of non-polar compound.
Yeah, excuse me, can you please repeat the question?
Sir, my question is that how the porous silicone material is giving the signal to non-polar compound.
Yeah, actually the response of porous silicon toward the non-polar compound or even polar compound, it depends on two factors. The first factor is the change of refractive index upon infiltration of analyte, I mean polar or non-polar compound. In polar solvent, the physicochemical properties, including the refractive index and the polarizability, is completely different with non-polar. That is the reason why we got some positive, increment in capacitance change, while in non-polar, the direction of the change of capacitance is opposite. This is actually depend on the physicochemical property of polar from non-polar to polar compound. Here, here the dielectric constant and the dipole moment, as well as the polarizability of the polar compound, is completely different from normal hexane and toluene.
Thank you, sir.
We have another question, I think, from Mr. Vakas.
Yes, I have a question.
Yes, please go ahead.
Dear sir, I want to inquire that can we make a green nanoparticles of titanium if it is possible?
Yeah.
Hello, can you hear me?
Excuse me?
Hello.
Yes, Vakas, please ask your question.
Can we make a green nanoparticles of titanium?
The main. Excuse me, the question is not clear for me. I couldn't catch.
Yes, again, I am going to repeat that. Can we make a coupling of green nanoparticles of titanium with some others? Like there is a number of methods we can make a green nanoparticles. How we can make a green nanoparticles of titanium?
Titanium nanoparticles actually can be produced in very simple chemical way using a gel technique. It's a well-known technique, or
yes,
or some hydrothermal technique. In our laboratory, we used some modified sol gel technique in which we used some block copolymer as a surfactant, because this kind of polymer act as a templating agent, and after formation we make some calcination of this synthesized titanium, and during the calcination kind of heat treatment, we get off from the polymer as a structure directing agent, and the remaining part is the titanium. Titanium will be changed from non-crystalline to crystalline, and in most cases we got mesoporous titanium.
Thank you. All right.
Do we have any other questions? If not, then let's thanks Professor Farid for such an excellent talk. Thank you so much, sir, for your precious time and such informative talk. Jazakallah khair. Thank you everyone for your participation.
Yeah, thank you very much, Dr. Siddiqui, and I thank all participants. Thank you very much.
Thank you. Bye-bye. You have a good day.
Bye-bye.